All right, let's jump straight in. Welcome to this explainer, where we're going to put on our data detective hats to uncover the exact difference between a B and an A star in Cambridge Physics 9702. Today, we're tackling a super foundational but honestly frequently mishandled area of the syllabus: scalars and vectors, adding and subtracting coplanar vectors, and resolving perpendicular components. But look, we aren't just looking at the physics today. We're going to break down the exact high-mark exam strategies you need to translate your theoretical understanding of magnitude and direction into actual, tangible results.
0. Yep, absolutely nothing. That is the shocking number of marks awarded for a perfectly calculated vector answer that completely ignores the context of the question. I mean, you can execute the most flawless trigonometry when you're resolving perpendicular components, but if you treat it as just an abstract math problem and forget the physical reality of the specific situation you're analyzing, the examiners will literally give you 0 marks. It is a really harsh reality of the Cambridge assessment framework. And the proof is right there in the principal examiner reports. They literally state the classic mistake is providing generic answers not specific to the question context. Always link every point to the given scenario. This is an absolute game changer. Examiners repeatedly warn that generic answers ruin grades, which creates massive stakes for anyone who's just rushing through coplanar vector questions. It tells us that superficial breadth isn't enough. You need analytical depth. Every single time you calculate the addition or subtraction of coplanar vectors, you absolutely must anchor your math to the physical scenario in the exam paper.
So let's dive into Section 1, the core concepts and what actually makes that A-star difference.
The syllabus explicitly states that top-performing students exhibit connected, conceptual understanding that is transferable to unfamiliar context. Basically, top-tier candidates don't just memorize formulas. They successfully transfer their understanding to entirely new complex scenarios. They don't just know how to find a resultant vector, they understand exactly how physical forces interact in the real world. When confronted with some bizarre, previously unseen physical scenario on test day, they don't panic. They just rely on their core principles, knowing that the physical laws governing scalars and vectors remain exactly the same.
Now, you might be wondering, what is the single examiner clue that changes a vector calculation completely? Well, in just a moment, I'm going to reveal that vital clue. But first, you need the analytical framework that makes that clue super obvious, because without it, you'll literally read right past the crucial data the examiner is hidden in the text.
Which brings us to Section 2, the framework, specifically our method mark strategy. To lock in those method marks, there is an exact 4-step sequence you have to follow. Step 1, concept. Step 2, evidence and data. Step 3, scientific reasoning. And Step 4, examiner wording. When you're analyzing coplanar vectors, you have to systematically deconstruct the problem using this sequence. Identify the underlying physical concept, pull the exact evidence from the text or tables, walk through your scientific reasoning step by step, and finally, present your answer using the precise terminology the examiner expects. To execute this properly, your systematic processing must follow strict conventions. 1. Identify key elements. 2. Apply relevant principles. 3. Execute with clear working. 4. Verify results. And 5. Present in an appropriate format. This procedural framework is totally critical. When you execute your analysis, the working has to be crystal clear. And honestly, perhaps the most forgotten step is verifying your results. You must always check your answers for physical reasonableness before presenting them. Like if your resulting force vector seems impossibly huge for the scenario described, you need to go back and check your steps.
Let's put this into practice with Section 3, flawed versus perfect answers. Think of it kind of like an exam heist. I want you to pause for a second and try to predict something. Spot the error. How does an ordinary vector calculation fail the principal examiner's standard? Think about everything we've just discussed regarding systematic analysis and evidence-based reasoning. Put yourself in the shoes of the examiner. The contrast between these two approaches is just brilliant. A flawed answer is a vague, generic calculation that completely lacks annotation. It's totally superficial, just blindly crunching trigonometry. But a context-specific, A-star answer, it follows the exact procedural framework. It uses clear notation, verifies reasonableness, and justifies every single mathematical step with the context provided in the question. The physics leads the math, not the other way around.
Let's move straight on to Section 4, Insider Intel, covering the top 3 examiner warnings. As a data detective, you have got to avoid these 3 fatal traps. Number 1, answers are too vague. Examiners want specific details. Number 2, students forget to check format and presentation. And number 3, answers are not specific to the context given. Remember, the assessment framework heavily prioritizes analytical depth. If your answer is vague, it shows a lack of conceptual understanding. If your format is messy, you lose the method mark. And if you ignore the physical context, like we saw right at the beginning, you risk getting an absolute 0.
Because, as the reports say, top-scoring candidates demonstrate evaluative thinking by questioning assumptions, considering different perspectives, and justifying decisions with evidence. Higher-order assessment objectives demand that you evaluate alternatives and always check your vector calculations. This quote beautifully summarizes what it takes to move from a basic descriptive level through analytical all the way up to an evaluative level. Top-scoring candidates don't just blindly trust their calculators. They question the assumptions, consider the evidence, and make justified recommendations based on real physics.
Finally, let's look at Section 5, the missing variable, which is linked practical skills.
So here is the ultimate question. How do you apply this exact vector framework to a linked, practical data analysis question? What happens when you are suddenly forced to apply these vector components to a complex, practical investigation design or a raw data table? Extracting data from texts and interpreting relationships from a table require the exact same foundational principles, but the cognitive load is so much higher. It's kind of like the final boss of the exam. You have to evaluate alternatives and compare approaches using actual experimental data.
Well, the next clue to cracking that is in our follow-up explainer. You can find us at Ace the Exams. That's at acetheexams_IGCSE to really excel in your Cambridge examinations. But until then, I want to leave you with this. The next time you sit down to calculate a vector component, ask yourself, are you just crunching abstract numbers, or are you actually describing the physical reality of the universe? Keep your analysis grounded in reality. Thanks for joining this explainer, and we'll catch you next time.